In this lecture, I want to discuss the question, how do we differentiate vectors? In particular, how do we differentiate vectors in curved space-time or space? After we learn to differentiate vectors, we'll differentiate the velocity vector to determine the acceleration of a time-like world line. So recall that a vector is a directional derivative operator and it lives at a particular point in the space or space-time. So here's my space or space-time, here's a particular point. We have our velocity vector will represent by a little arrow, and it's a derivative operator, so it acts on functions that are defined within a neighborhood of this point, and what it gives is the derivative of the function along the direction of the vector. Okay, now this is a single vector that sits at a point. We often work with vector fields, which is a field of vectors, so a vector at each point in the space or space-time. For example, let's take a space with coordinates x and y, and let's consider the vector, I don't know, maybe x plus y d by dx plus x squared d by dy. And we can plot a graph. This is the xy plot, and at, for example, the point x equal 1, y equals 0, what is this vector? Well, 1 plus 0 is 1 d by dx plus 1 d by dy. So this would be an arrow like this. We can pick another point, say x equal 2, y equals 0. This would be 2d by dx plus 4d by dy. So we'd have a relatively much larger arrow here. And let's pick one more point, say 0, 1. So this would be 1d by dx plus 0d by dy. So that would be something like this. So at each point in the space we have a vector, and that's referred to as a vector field. Let's say we want to differentiate a vector field along some curve. So here's a curve. Let's say this curve is given by the coordinates as some function of a parameter lambda. And here's one point on the curve. Let's call this point P. And since this is a vector field, we have a vector at each point. There's the vector at point P. Here's another nearby point Q. And here's the vector at point Q. And let's say that this point P has parameter value lambda 0, and this point Q has parameter value lambda 0 plus delta lambda. So it's a small change in lambda. I'm imagining the points P and Q to be close together. Well, how do we define the derivative of this vector field at P? We'll call the vector field V at point P. Well, naively, we would say that the derivative of V with respect to lambda is given by the limit of, we take the vector at a nearby point Q and subtract the vector at point P and divide by delta lambda. This definition is wrong. In fact, it's not well defined. It's not well defined because we actually don't know how to subtract a vector that sits at one point P from a vector that sits at another point Q. All right, now if we have two vectors that just sit at the same point in a space or space-time, we know how to subtract them. Let's say we have a vector A, which expanded in a coordinate basis is a mu d by dx mu, and another vector B if these points sit at the same, if these vectors sit at the same point, then a minus b is just a mu d by dx mu minus b mu d by dx mu, and we can factor out the d by dx mu and just write a mu minus b mu d by dx mu. So we see to subtract two vectors that sit at the same point, we just simply subtract their components. But we can do this, we can factor out d by dx mu because these vectors sit at the same point. It's the same d by dx mu. So these two factors are the same. Assuming that a and b sit at the same point. On the other hand, if the two vectors don't sit at the same point, then the basis vectors are different. Here's a quick example. Let's just look at polar coordinates in flat 2D space. The basis vector at the basis vectors in polar coordinates at this point look like this. This is d by dr, this is d by d theta. But if we pick another point, say over here, then d by dr points in this direction, and d by d theta looks like this. All right, so we can't simply take a vector at this point and a vector at this point and subtract those two vectors by subtracting their components. That doesn't work. We need a more sophisticated notion of what it means to subtract vectors at two different points. So what we need to do, if we go back to our naive expression for the derivative of this vector field at point P, is instead of taking the vector at point Q and subtracting the vector at point P, we need to first transport this vector at Q to the point P so that they sit at the same point, and then we can subtract them. So we need to transport the vector at point Q to point P, and then we can subtract. So how do we transport vectors? From one point to another? Well, in flat space, we know how to do this. We just move the vector around, making sure that we keep it parallel to itself and that we don't change its length as we move it. We do the same thing in curved space or curved space-time, but there it's a little bit more complicated because the definition of what it means to stay parallel to itself and keep its length unchanged is defined by the metric. This process is referred to as parallel transport. So the real definition of the derivative of a vector field at some point P is d by d lambda is the limit of, take the vector at point Q and parallel transport it to point P, and I'll denote that with a little Q arrow P. So that means the vector Q transported back to the point P. Then we subtract from that the vector that sits at point P divided by delta lambda. So let's see what this definition tells us. First, let's expand these v's in a coordinate basis. So we can write this as dv d lambda equals the limit of v mu d by dx mu, the vector that sits at point Q, parallel transported to point P, minus v mu d by dx mu at point P, all divided by delta lambda. Now, the v mu's here are just numbers, right? So they're not affected by this transport from Q to P. That only affects the vectors. So this is v mu at point Q times d by dx mu at point Q transported to point P minus v mu at point P times d by dx mu at point P. All of that divided by delta lambda. And I forgot the mu's here and here. So let's look at one of these basis vectors transported from Q to P. So for example, let's look at d by dx 0. All right, that's the basis vector, one of the basis vectors that sits at point Q and is transported to point P. So this is a vector that sits at point P, and like any vector, it can be expanded as a linear combination of basis vectors at point P. All right, so we can write this as linear combination where the components of this vector at point P are these C's, C nu. Okay, and we of course can do this for every one of the basis vectors. So in particular, let's write d by dx mu transported from point Q to point P is, for each value of mu, we have a set of coefficients C nu, so we'll call those C nu mu, then times d by dx mu at point P. Actually, that index mu should be a nu. Let me erase that. So it's this index nu is being summed over, and the index mu is a free index. We're free to choose 0, 1, 2, or 3 for that index. All right, now putting this in for d by dx at Q parallel transported to P, we find that dv d lambda is the limit of v at point Q, the components of v at point Q, times C nu mu d by dx nu at point P minus v mu P d by dx mu at point P. And all of that's divided by delta lambda. So what I want to do now is factor out the common factor of d by dx at point P. Before I do that, I need to line up the indices. So let me replace these indices mu with nu. So we'll call this v nu P times d by dx nu. And now we have a common factor we can remove. This is limit. Let me bring the 1 over delta lambda out front. vq mu c nu mu minus v nu P, all times d by dx nu at point P. So what we have here is a vector. It's the derivative of v with respect to lambda, but it's a vector itself that sits at point P. And in fact, here's the expansion of that vector in terms of the basis vectors at point P. So these would be the components of the vector. The components of dv d lambda. And let's write those components as, let's just write dv d lambda parenthesis mu for the components of dv d lambda. So this is the limit of 1 over delta lambda v mu q c nu mu minus v nu at point P. Okay, let's take a closer look at the components of the vector field V at point Q. These were just the components of the vector field at the point we called with parameter value lambda naught plus delta lambda. Right, so we can now expand that since we'll be taking the limit as delta lambda goes to 0. Let's expand this into Taylor series. This is v mu at point lambda naught plus the derivative of v mu with respect to lambda at lambda naught times delta lambda. And then of course we have higher order terms that will drop since we're taking the limit as delta lambda goes to 0. right? This first term, v mu at lambda naught, is just the components of the vector field at point P. We have plus the ordinary derivative of these components with respect to lambda at point P times delta lambda plus higher order terms that drop out. All right, so if we put that in for v mu q, what we find is the components of dv d lambda are the limit of v mu p times, that's this term, times c nu mu plus this term, partial v mu with respect to lambda at point P times delta lambda times c nu mu minus v nu p. Okay, this term, well, let's take a look at, let's think for a moment about what these c's are. We haven't specified them yet, but we know that they represent the change in the basis vectors at Q when they're parallel transported to point P. Now, if points Q and P are really, really close together, then the two sets of basis vectors should be close to one another. So in other words, these coefficients C should be close to the Kronecker delta. So this should actually be something Kronecker delta plus higher order terms of order delta lambda. So in this expression where we're ultimately taking the limit, we only need to keep terms of first order in smallness in delta lambda in the parentheses here. We already have a factor of delta lambda. So all that means that I'm free to replace this c nu mu with Kronecker delta nu mu. So this is the limit of 1 over delta lambda v mu at point P c nu mu plus partial of v, and now replacing c with the Kronecker delta, and we of course sum over mu. The only term that survives is when mu is equal to nu, so I'll just write this as partial of v nu with respect to lambda at point P times delta lambda. Right, and then the last term here is v nu p. All right, let's bring this term out by itself. We have the components of dv d lambda. Let me pause for a moment because I see I've made a mistake. This index should be nu, and I can tell because the right-hand side, the free index, is the index nu in each of these terms. The index mu appears here, but it's being summed over, so it could be really called anything, alpha, beta, anything you like. Right, so the free indices need to balance throughout an equation. Let me see where I made that mistake. So the mistake came here when I was identifying the components of dv d lambda as this expression. What I did is I stripped off d by d nu. So, and nu of course is being summed over in this equation, but when I removed d by d nu, it left a free index nu, and so this index right here should have been nu. Okay, and again, free index nu, free index nu. And in this equation as well, this should be nu. All right, so now if I continue, what I'm doing is I'm bringing this term out front. The delta lambdas cancel, and we have the ordinary derivative of the components of v at point P plus the limit of 1 over delta lambda of this term minus this term. And let me write it in the following way. Let's write it as c nu mu minus Kronecker delta nu mu times v mu p. So I've factored out a common factor of v at point P, the components of v at point P. But notice in order to do that, I had to, in essence, change this v nu into a v mu times a Kronecker delta mu nu. And that's the Kronecker delta here. Now this result holds for any curve through the space or space-time. So in particular, we can let the curve be one of the coordinate lines. So for example, we can set lambda equal to, say, x alpha and write dv dx alpha. So that would be the derivative of the vector field along the coordinate line x alpha, and we take the nth component of that, and that's equal to the ordinary derivative of the components of the component of the vector field v nu with respect to x alpha plus the limit of c nu mu minus delta nu mu over delta x alpha, all of that times v mu, the components of the vector v. And it's understood that this is, everything here is evaluated at a common point P. Now this combination, which involves the C's tell us how the basis vectors change when we move from point to point. This combination is given a symbol capital gamma, and it has three indices, nu, mu, and alpha. All right, so we can write our result here as dv dx alpha nu equals partial of v nu with respect to x alpha plus gamma nu mu alpha v mu. Okay, the gammas are referred to as the Christoffel symbols. And this quantity dv dx is referred to as the covariant derivative. All right, and we'll invent a little bit more compact notation for this later on. But let's just be clear about what this expression means. What this is, so here's coordinate lines. So this is coordinates, say, x1, x0. So we have a vector field. So there's a vector at each point. And in particular, here's the vector at this point. Let's say this is the vector at this point. What this represents is taking, if we want to differentiate this vector field at this point right here, P, what we need to do is parallel transport the vector from a point Q, which in this case is displaced along the x1 coordinate line. So this would be dv dx1. Okay, so we parallel transport this vector. So we bring it over to this point P, keeping it parallel to itself and not changing its length. And then we subtract. We subtract this green vector minus the red vector. Right? And in elementary physics, we would draw that difference vector as a little arrow from tip to tip of these two vectors. So what this is with the nu is it's the components of this little blue vector at the point P. And you can see that in a general curved space or space-time, the components of this vector, this difference vector, are given by just the derivatives of the components of the vector field plus another term involving these Christoffel symbols. Now let's find out what these Christoffel symbols are, the big gammas. In order to figure that out, we need to take a closer look at what we mean by parallel transport in a curved space or space-time. Well, parallel transport will keep the length of a vector unchanged, and the length of a vector is defined by the inner product of the vector with itself. That would be the squared length. Okay, and the inner product is determined by the metric. Right, and of course the metric can be used as an inner product between two different vectors, say v and w, And that's the generalization of the dot product, so it tells us the angle between these vectors. Now, this is just an ordinary function, assuming v and w are vector fields. This is a number or a value at each point in the space or space-time. So this is an ordinary function, and we can differentiate this along any particular direction, say along a coordinate line x alpha. So let's do that. Let's take the derivative with respect to x alpha of g acting on v and w. Now, we know we can write g acting on v and w in terms of components. The components of the metric g mu nu wired together with the components of v and the components of w. So that's v mu w nu. And now this should satisfy, like any derivative, this of course satisfies the product rule. So this is the partial of these components g mu nu with respect to x alpha, v mu w nu, plus g mu nu partial v mu with respect to x alpha w nu, plus g mu nu v mu partial w nu with respect to x alpha. Now here's the key piece of reasoning. Let's say that this vector field v is not just any arbitrary vector field, but let's say it's constructed in the following way. Let's say that we start with a vector at this point, and we'll call the vector v, and then we extend it into a vector field, a vector at each point in this region, by parallel transporting this vector. So v is defined by parallel transport. It's parallel transported to form a vector field. All right, now that means that if we differentiate v, the vector field v, along any direction, we'll get 0. So dv d lambda, or dv d x alpha, if you like, or any other direction, is 0. And since, remember, the derivative, the covariant, this is the covariant derivative. It has components that are equal to the ordinary partial derivatives of the components of the vector field plus the Christoffel symbols. The Christoffel symbol term like this. So for this vector field that's formed by parallel transporting a single vector all around, this is equal to 0. And we can do the same thing for the vector field w. We can start with a vector at some point, this point, or it could be a different point, and we define the field as obtained by taking this vector and parallel transporting it to other points in the neighborhood of that point. All right, so then we also have dw by dx alpha, the muth component, is equal to partial w mu with respect to x alpha plus gamma mu nu alpha w nu equals 0, since w has been parallel transported throughout the space. So if we take a look at what we're calculating here, this is the derivative of the inner product between v and w. So this is the difference between the inner product of, here's v and w at one point, and here's v and w at a nearby point, and these have been parallel transported. So the inner product, which is a generalization of the angle between the two vectors, that inner product shouldn't change. So since because of these vector fields have been parallel transported. So the left-hand side here should be 0. All right, so let's set the left-hand side equal to 0, and then the right-hand side, we can replace these derivatives of v and w with respect to x alpha using these expressions. So let me write this out carefully. We have 0 from the left-hand side equals partial g mu nu with respect to x alpha v mu w nu plus g mu nu partial of v mu with respect to x alpha times w nu plus g mu nu v mu partial w nu with respect to x alpha. And now we'll replace partial v mu with respect to x alpha with minus gamma mu alpha. There's a v here. There's a repeated index nu, but I don't want to use the index nu because I'm already using the index nu here and here as a repeated index. So let me come up with another Greek letter, say beta. All right? And similarly, for this expression, this is minus gamma. The upper index is nu instead of mu. We have a lower index alpha, and then we have a repeated index on the first lower slot of gamma and w. And let's not use the letter nu, again, because it's being used here and here. We'll use the letter beta. All right, so this is equal to partial mu nu, partial of g mu nu with respect to x alpha v mu w nu minus g mu nu times gamma mu beta alpha v beta w nu minus g mu nu v mu gamma nu beta alpha w beta. Notice I have a common factor of v and w in each of these terms, and I'd like to factor those out. But before doing so, I need to make sure the indices line up. So here we have indices mu and nu on v and w. Here it's beta and nu. So let me change this beta to a mu, but I'm already using mu here, and I don't want to confuse these sums. This is really a double sum. It's a sum over mu and a sum over beta. But what I can do, since these letters are arbitrary, they're just being summed over, I can swap beta and mu. So I can change this beta to a mu, this beta to a mu, and then these mu's can be changed to anything I like. So why not just use beta for those? And likewise here we have we'd like this index on w to be a nu to correspond to these terms. So let's change this to nu and this to nu. And in order to not confuse that sum with the sum over nu here, we'll change this to something else like beta. All right, so with those changes in the index names, we have partial g mu nu with respect to x alpha times v mu w nu minus g beta nu gamma beta mu alpha times v mu w nu minus g mu beta v mu then times w nu gamma beta nu alpha. All right, so we have these common factors of v mu w nu. Now this relation should hold for any vector fields v and w that are parallel transported throughout a region of space. So in order for that to be the case, then the coefficient of v mu w nu must vanish. Okay, so this implies the same expression with v mu w nu removed. That's partial g mu nu with respect to x alpha minus g beta nu gamma beta mu alpha minus g mu beta gamma beta nu alpha. So this equation relates the Christoffel symbols, the big gammas, to derivatives of the metric, and of course the metric itself. So we'll solve this in a minute, but before we do that, let's take a close look at this equation. notice there are three free indices in this equation. So we have a mu, a nu, and an alpha, and we're free to choose any values, 0, 1, 2, or 3, for each of those indices. On these terms, the index beta is a repeated index, so it's being summed over in this term as well as this term. But again, we have three free indices, mu, nu, and alpha. And in four-dimensional space or space-time, the free indices can take on values 0, 1, 2, or 3. That's four different possibilities. So we have, how many equations does this actually represent? Well, mu can take on any one of four values, nu any one of four values, and alpha the same. So that's 4 times 4 times 4 is 64 equations. But actually, remember that the metric tensor components are always symmetric. So if we think of this G mu nu as a matrix, then this is not, it's a 4 by 4 matrix, but there are not 16 independent entries because it's symmetric. There are only 10 independent entries. So the total number of equations here is really 4 from the 4 possibilities of alpha times 10, namely the 10 entries in this symmetric matrix G mu nu. So that's 40 equations. And how many unknowns are there? The unknowns here are the Christoffel symbols, the gammas. And there are 4 times 4 times 4, because there are 3 indices. That's 64 unknowns. The gamma, beta, nu, alpha. All right, so we don't really have enough equations here to determine all of the Christoffel symbols, but only some of them. So let's take a look at this. The Christoffel symbols, gamma, beta, mu, alpha. Just pick a value for beta and look at this. Think of this as a matrix, a 4 by 4 matrix in its lower 2 indices. We can always split any matrix up into a symmetric and an anti-symmetric piece. So for example, we can always write this as gamma beta mu alpha plus gamma beta alpha mu plus gamma beta mu alpha minus gamma beta alpha mu. All right, so this quantity, again, I'm just ignoring beta, or just pick a particular value for beta and just looking at this as a 4 by 4 matrix in the lower indices. This is explicitly symmetric. So this is the symmetric part of big gamma. And this is antisymmetric. So it's antisymmetric in the sense of a matrix. And in terms of these indices, it means that if we swap alpha and mu, then we get an overall minus sign in this expression. So looking at this symmetric part, how many of these are there? How many components are there? Well, there's the 10 components in a symmetric 4 by 4 matrix times the 4 possible values of beta. So there are 40 of these. And how many of these antisymmetric components are there? Well, in an antisymmetric 4 by 4 matrix, there are 6 independent components times the 4 possibilities for beta. That's 4 times 6 is 24. All right, so the 64 unknowns can be split up into 40 unknowns for the symmetric part of gamma and 24 unknowns for the antisymmetric part of gamma. So these 40 equations that we've written down up here, we'll use those to solve for the symmetric part of gamma. So what do we do about the antisymmetric part? That's this part. This part of the Christoffel symbols is usually referred to as the torsion. So this is actually given the symbol T, beta, mu alpha. And if we think of this as a matrix in the lower two indices for a fixed value of beta, it's anti-symmetric in these lower two indices. Well, the standard assumption in general relativity is that the torsion vanishes. So we will assume that T, the torsion, is equal to 0. I'm not going to try to give any deep justification for this assumption. You can do an internet search and see that this is a pretty common topic of discussion, and people have various arguments for why it's natural to assume that the torsion vanishes. To be honest, I don't find any of those arguments to be particularly compelling. But ultimately, keep in mind that what we're doing is we're building a theory, Einstein's general relativity, and whether the theory is right or wrong is up to experiment to decide. And I think it's fair to say that at this point in history, we don't really have any compelling experimental evidence that the torsion is not 0. So we'll go ahead and assume that the torsion is 0, and what that means then is that the Christoffel symbols are symmetric in their lower indices. So now let's return to the equation we're trying to solve, and I'll repeat it here. It's 0 equals the derivative of the metric components g mu nu with respect to x alpha minus g beta nu gamma beta mu alpha minus g mu beta gamma beta nu alpha. Now, before I solve this, I want to introduce some simpler notation. First of all, for derivatives with respect to the coordinates, let's use the symbol partial alpha. So that's just shorthand notation for partial derivative with respect to x alpha. And I also want to shorten this combination, make a shorthand notation, and call this gamma nu mu alpha. And this combination would be gamma mu nu alpha. Okay, remember the rationale for this comes from the fact that we can always associate a covector with any vector by using the metric. So we fill one slot of the metric with a vector, and that leaves us an operator that operates on vectors. So this is a covector. And we denote this in components as g mu nu v nu. So these are the components of a covector, and we usually denote that the components of that covector is v with a lower script mu. So, and loosely speaking, we refer to this as lowering the index. All right, so I've done the same thing here. I've just lowered the index, this index beta, using the metric. Now, strictly speaking, the Christoffel symbols are not a vector, but just as a notational device, we can still make this definition. So here, the repeated index is beta, and I've replaced beta with this index mu and put it in a lower position. And the usual convention for the Christoffel symbols is when we lower the index, we put it into the sort of slot here that precedes the other indices. And same here, we've moved that index down and called it nu. All right, so now with this shortened notation, our equation can be written as partial alpha g mu nu minus gamma nu mu alpha minus gamma mu nu alpha. In this equation, alpha, mu, and nu are free indices, so we can, and we can call them anything we like. For example, we could change alpha to beta throughout this equation. So let's do the following. Let's rewrite this equation, but let's make the following changes in the choice of index names here. Instead of alpha, let's use mu, and instead of mu, let's use nu, and instead of nu, let's use alpha. So in each of these terms, we'll replace alpha with mu. We will replace mu with nu, and replace nu with alpha. All right, so if we write this equation out with this index pattern, we have partial mu g nu alpha minus gamma alpha nu mu minus gamma nu alpha mu. Now let's write this down a third time, and we'll swap indices again, letting mu become nu becomes alpha, and alpha becomes mu. So we have partial g minus gamma, and from here we'll let mu become nu. There's a third index here is mu, and that becomes nu. All right, this nu we're replacing with alpha. So this nu becomes alpha, and here it's the first index, alpha, so I'll leave a little gap. And finally, we have the index alpha becomes mu. So here alpha becomes mu, alpha becomes mu. So now I have this equation written three different ways. It's the same equation, just different index names. And I'm going to combine these three equations by adding this one, subtracting this one, subtracting this one. So we'll take this equation, minus this equation, minus this equation. And when we do that, notice some of these Christoffel symbol terms will vanish, will cancel. Remember that Christoffel symbols are symmetric in their lower two indices, and we've lowered the upper index. That became the first index. So these Christoffel symbols with all lower indices are symmetric in their second and third indices. So for example, this Christoffel symbol with nu mu alpha is equal to nu alpha mu, because these differ just by swapping the second and third indices. So when I combine these equations with a plus sign for this equation and a minus sign for this one, this term will cancel this term. And similarly, this term will cancel this one, because again, they just differ by swapping the second and third indices. So those two cancel. So what we're left with then is 0 equals partial alpha g mu nu, and we're subtracting this equation, so we'll have minus partial mu g nu alpha minus this term is partial nu g alpha mu, and we're left with some Christoffel symbols here. And notice these are actually the same. By symmetry in the second and third index, we can swap nu and mu and write this as alpha mu nu, just like this one. So along with these minus signs, cancel these minus signs, so we have plus 2 gamma alpha mu nu. So now we can solve for gamma alpha mu nu. That's equal to 1/2. Let me write these two terms first. We have partial mu g nu alpha plus partial nu g, and well, g is symmetric, so let's write this as alpha, as g mu alpha, minus this term is partial alpha g mu nu. All right, remember this is shorthand for g alpha beta gamma beta mu nu. All right, so if we want to actually solve for the Christoffel symbols themselves with one upper index and two lower indices, we just need to multiply this equation through by the inverse of g. So we would multiply both sides of this equation by g alpha, and let's come up with another Greek letter, say sigma. So let's multiply both sides of this equation by g alpha sigma. All right, when we do that, notice these two factors. This is g alpha sigma times, so that's the inverse metric times the metric itself, just gives us a Kronecker delta beta sigma. And then we have a sum over beta here and here. So it's the usual argument in that sum. The only non-zero term is the one in which beta is equal to sigma. So what we have on the right-hand side is gamma sigma mu nu. Okay, so let's put all that together. We find gamma mu nu sigma is equal to 1/2 g, I'll write that term first, and since inverse metric is symmetric, I'm going to swap the indices here and write sigma alpha times partial mu g nu alpha plus partial nu g mu alpha minus partial alpha g mu nu. So here is our final result. These are the Christoffel symbols written explicitly in terms of the metric and derivatives of the metric. And remember, we're assuming no torsion, which means the Christoffel symbols are symmetric in their lower indices. And you can see that here on the right-hand side. The right-hand side is explicitly symmetric, and it's in mu and nu. This term is symmetric in mu and nu because the metric is symmetric. And these two terms together, you can see that if you swap mu and nu, that these two terms just swap places. So this is our expression for our symmetric in its lower indices Christoffel symbols. So let's recall what we use these for. This is part of the definition of the covariant derivative. All right, so we have the covariant derivative of a vector field along the coordinate direction x alpha. The nth component of that is given by the partial derivative of the components v nu with respect to x alpha plus these Christoffel symbols, gamma, nu, mu alpha, v mu. And by the way, since the Christoffel symbols are symmetric in the lower two indices, we can write those two indices in any order we like. We can write this as alpha mu. All right, and the meaning of this is we have a vector field. So this is the x alpha coordinate line, and we have a vector field. So here's the vector v at point Q, and here's the vector v at point P, and we are defining the derivative of this vector field by parallel transport. So we're parallel transporting this vector from point Q back to point P. So here's the parallel transported vector from Q to point P, and then we're subtracting them to get to define our derivative. So that's the notion of the covariant derivative, and it relies on this idea of parallel transport. And before we close for this lecture, let me introduce a more common notation for this. Remember, the meaning here is the derivative of the vector field along this coordinate line, and that vector field can be expressed in a coordinate basis. So this is the nth component of that vector field. The standard notation for the covariant derivative is del alpha, that's the del symbol or the nabla, v nu. And we can also write this as partial alpha v nu plus gamma nu alpha mu v mu. But just remember that the meaning of this expression is this is not a derivative operator acting on the components of the vector. This is really a derivative operator, the covariant derivative, acting on the vector field v, and we're looking at the nth component of that vector field.